had one, Floyd, we had one presentation. Dan Lane decided to hold off on his presentation until another time. So it's not quite as crowded as it was expected to be. So I want to go through introductions. Always introduce the board members. I think most of them are, if not all of them, are here tonight. I think we are all here, except for I don't see Rick on here. Oh, there he is. Hello, Rick. There you are. Rick Ambley, K0GD, lives up the Black Forest. Paul Sabone in O0T up in Denver area. Bill Miller, and he vice president, and lives here in Colorado Springs. And let me see, Floyd Glick, our secretary, lives here in town. And Don Latham, lives up in Montana, Frenchtown, Montana, I believe. So welcome all the board members. We do have a quick note. We do have board elections coming up this year, electing 3 board members. We have open nominations right now. We have 4 people nominated for 3 positions. They've all been nominated in second. Those nominations include Don Latham, current board member, Paul Sabone, current board member, and we have Bill Thomas, our webmaster, and we also have Alex Nerson, K6VHF, living in, there you are, living down in Chandler, Arizona. So everybody's on here, and we'll have more about that later on to the voting for the voting members. I want to welcome Gary Agrinet back in again. I haven't seen him in a while. He's a busy guy working out of Schreiber Air Force Base. He can't tell you what he does, or he'd have to kill you. So that's one of the secrets he does out there. So we won't advertise that, except here on the internet. Let me see who else is in here. Derek. Derek doesn't look like the Derek I remember. Is this a new Derek?
I normally can't attend many Monday meetings, but I've done a few of them now.
Okay, yeah. And where are you located?
I'm in Hudson, Colorado.
Hudson, okay. Yeah, Derek Brown was the other Derek I was thinking of, and he lives here in town. So Derek Brady is that what you said up in
Yeah.
Hudson? All right. I want to welcome Michelle in San Diego. Thanks again, Michelle. I forgot to, I had an email sent out to you, but never sent it for your presentation last month. Kathy and Rick Wildman out in Peyton, Colorado, or Falcon, actually. And let me see who else. Burton in 6UG out at Quartz Fest in the deserts of Arizona. He normally lives, when he's not camping in the desert, lives in Rockland, California. So anybody else that I missed want to introduce yourself? Is Doug on here, Doug Lieber?
Yes.
Oh, I just missed you somewhere. There you are. Okay. Okay. Doug's the first one on the list. We had our first official high school orientation, and Doug headed up this event. So Doug, if you're ready, you can tell everyone what happened last Wednesday down at the Flischner site.
Yes, we welcomed about 20 people, 16 students and 3 teachers. The students were from participating in science fair at Las Animas High School or in Science Olympiad. And most of them were undergraduate, not undergraduates, but were sophomore and juniors who were attending. And only one of them had any previous background in astronomy. She had taken a course at the Otero Junior College, and that was a internet course. So it was a pretty raw group, and Bill Miller gave a presentation on a bit of the history of the Flischner site and an introduction to radio astronomy and some of the research that we've conducted here. And then Ray, we split them into two groups, and one group went and Ray gave them a tour of the control room, and demonstrated moving the dish in the tracking system. And the other group went with Paul Sabon and into the bunker and listened in on some QSOs that were Paul was making. And they seemed to really enjoy. It was not great. We didn't have it set up real well for them all to see the action on the with the radio because of the confines of the bunker. But they seem to enjoy that activity quite a bit. And we got some good questions from the students in to Ray in the control room. And Myron was there, and Roger Oakey was there as well. So all in all, I haven't spoken with the teachers yet. I'm going to contact them this week and get some feedback about what the students what they thought of it. But I was pretty pleased with our first effort getting it together, and I'm looking forward to doing some more.
Paul, do you want to comment? You were kind of heading this thing up, helping Doug out get this thing started.
Yeah, okay, sure. Yeah, the boys, can you hear me okay?
Yes.
Okay, good. Yeah, the kids came downstairs. By the way, there was, let's see, well, I don't know how many students. I thought there was 17, but who's counting?
16 had signed the list.
Yeah, I counted 19 students and 4 adults, 3 of which were teachers.
Okay.
And two were boys. The rest of them were girls. So there's
Yes.
definitely a swing here towards the girls for astronomy, I guess, or for science. I was really pleased with that. And the bunker was about 8 degrees Celsius, and so they didn't want to stay down there too long. Everyone huddled around the heater that we put up, the big 220 volt heater, and it wasn't quite enough to warm the place up. So they were, although they were very interested in, and we got a couple of them to call CQ on the radio, and we didn't get any response, but they enjoyed handling the microphone and learning how to call CQ. I wrote out what they should say. So they did all that, and they seemed, the girls were, the guys were very shy. They didn't want to get on, but the girls were ready to talk on the mic, and they were very happy to get out of there into their warm bus.
Yep.
And we took the bus back and forth between the bunker and the building because it was so cold and the wind was so strong. Oh, we were like popsicles. So
yeah. Paul, can I share pictures here?
Sure, please go right ahead.
Yeah, the
All right.
wind was blowing about 30 knots or 30 mile an hour down there that day. So the wind chill was pretty brisk.
Okay, can you see this?
Yeah.
Okay, that's Myron in the room. This is the whiteboards we set up and the tables and the new chairs that were donated by Rob McMasters. We picked these up at Costco last week and had it all set up when they got there, and set up a projector in the rafters and had the screen. And this is the radio room in the main control room. Had our posters up there. Paul and Ray showed the console. There they are on the console. There's the kids having sack lunch before the presentations. There's all the teachers standing around, the kids having their lunch. Here we go. And you can see it's mostly girls. I think there were, I counted 3 boys and I believe 16 girls altogether. Here's their bus in front of the dish. They took the bus back and forth to the bunker. There's everybody getting their shoes on and off, and we made them take their shoes off and put on booty protectors so we didn't track up the building. That was great, Paul. I appreciate that. There's everybody outside the dish. So if you count them, I think there's 19. And you can see them all shivering around the dish. Lots of dish pictures. There's Roger at the console. Myron. There's all the chairs put away. We cleaned up the place and put it all away, and everything was good. So here we are doing a presentation in PowerPoint, and there's Ray doing the demo on the console. So that's about it.
Yeah, it was a windy day, and we were out of there probably by 4 o'clock, weren't we? About 4 o'clock or so.
Yeah.
Well, we were down there, but it was
sign back there.
environmentally, it was a challenging day to be down there with all that wind, and that's why we was fortunate enough to use the bus back and forth to the bunker. And the adults I talked to seemed to enjoy the site, and they were really interested in maybe possibly doing more of this in the future.
Mhm.
So we'll see how that goes. I think Paul, Doug's gonna follow up with the local Kiowa County newspaper, maybe to get an article in there.
Yeah,
How's that coming along, Doug?
I'm drafting it.
Good.
Yeah, to get it done. She needs it by Thursday.
Well, she probably needs it before then in order to get it in, placed in
Yep.
the newspaper. They go to print on Thursday, or that's when they, that's when they close it out. So it's probably safer to get it if you can. If you need help, let me know.
But
Will
yeah,
do.
questions about this event, say it was our first effort at it, and it went fairly smoothly, really. The time allotted was what, 2 hours on site? So we managed to fill that 2 hours up and then some probably. So they were on their way back to Los Animas by 3:30. So they met their timeline as well. So thanks again for Roger coming down. He arrived a little late, but that was good for you, considering you weren't going to arrive at all, but you got there. So if we close this one out, I forgot to mention at the start of the program here that our Michael Lowe, our lifetime member, he resides in Waverly, Texas now. But his wife, Gail Lowe, who was really active with the DSES, he was a board member and secretary years ago, but she passed away on December 12th. And I had called Michael Lowe on the way back from this event with talking to Michael and telling him, and he was real excited to hear that we had our first high school or educational event. He had always was talking about that all the time he came to the site down there. So he was real excited. However, the bad news was I knew his wife wasn't doing well when I talked to him back in September, but Gail Lowe, she passed away of issues related to Alzheimer's and dementia, which really surprised. And he said that happened so quick that he couldn't believe it. So we pass our condolences on to Michael. Michael was the main force behind getting the Flischner site. He did all the legwork, corresponded with the Paul Flischner in New York, set up the attorneys in Colorado, and drafted the license agreement for the site. We got a quick claim deed for 5 acres. So that was done by Michael Lowe. And so we really appreciate his past efforts. He's one of the 5 life members that we have with the organization. So I'll continue with the agenda tonight. I think we deleted, I took Dan Lane off. He has a pretty good, at first time towards the end, he can give you a brief update on what he's doing. Then he'll give a more detailed presentation at the next meeting. So Ray, talked to me about 2 weeks ago saying he would like to do this presentation. So Ray, are you ready for this?
Oh, there, I finally found the mic button. Yeah, so tell me how I'm going to do this now. I've got, I would do a share screen, but do I put the
When you hit the share,
PowerPoint presentation down here first or what?
yeah, you should have the power presentation open up already.
I didn't have it yet opened up, but it will be opened up very quickly, I think.
And then once you get that open, you can do the share, and you should see a sub screen there on your. then that's what you click on that, then share it, highlight it and share it.
Yeah, it's still getting it ready here.
Okay.
Okay. And so now,
Let me, quick to Bill Thomas, have we gotten much of these programs to you to put on the website via PowerPoint, Bill, or is that a work in progress?
No, so Floyd's done a great job of getting all the presentations to me. They're all loaded on YouTube, but only the science meetings, actually edited versions of the science meetings, are made public.
Okay,
Any member who misses a meeting and wants a link to one of the hidden videos, all they have to do is email me and I can send them a link.
all right. Thank you for doing that.
now do you see anything yet?
Nope, have you hit the share button with
I will hit the share button.
you
There's
got
the
a-
share button.
You should see a small screen. There you go.
You can see that. So you need to expand that to a bigger size.
The small screen.
You picked your whole background, all your backgrounds showing.
Yeah, just increase the size of that window, that PowerPoint.
Yeah.
Upper right-hand corner.
I don't know how to do that yet, I guess.
Square in the upper right-hand corner, click that square up at the top on the right-hand corner.
Well, that's not moving. Let me see here.
Yeah. Upper right-hand corner, next to the
Get that away.
X of that window.
So I got something that says leave meeting up there. So
You can do that. You can back out and pick it again.
and say okay up there or something.
Yeah, there should be like a little.
Okay. Now
Now you could just share that particular window. You don't have to share the entire screen. So if you can see that window in one of your
like
monitors,
that more.
like
There you
that,
go.
there you go.
There you go.
So you can just play it from there if you want.
Okay. I'm gonna put that up.
Ray,
Yeah.
you also might try at the very, very bottom. There's an icon that looks like a screen that's pulled down just to the left of the 95%. Do you see the 95% at the bottom?
Yes.
Just to the left of that, there's a little icon that looks like a screen. If you click that, we should get it full screen.
Yeah, it'll expand.
Maybe this guy right here,
No,
reading
no,
view.
no, no.
Far
No.
right corner.
Just to
Normal?
the left of 95. None of those. None of those. There you go.
Slideshow? No, let's leave it alone. Okay, am I breaking up as bad as I hear you guys?
No, you're doing fine.
Because I've lost the audio pretty much.
Oh, we can hear you fine.
Do you hear me okay?
We
Yeah,
hear
you're
you
solid,
fine.
Ray. Yeah.
Boy, it's all broken up. I don't hear that very well.
Ah,
I heard that all right.
Yeah, we hear you fine.
Okay. If you can hear me okay, I'll go ahead and start doing it. Give me a thumbs up. Okay, got a thumbs up. Okay, what I want to do is talk about, come up with a few topics that I'd like to discuss over the next few months. And one of them, the first one, is the cascade noise figure. And that's an equation by Friis. And I wanted to discuss it a little bit, and then I'll tell you how to do it without going through the equation. But quite often the comments arise about how we do the preamps down at the site. And a preamp here, I'm referring to something that is extra from a regular radio. It's something that you mount up at the feed antenna. And so there's very little loss in front of the front stage. And so I'm going to go over the equation here a little bit, talk about that for a few minutes, and then we'll go on through and I'll give you some examples and where to get the equation, where to get a calculator for it. So if you can see the cursor a little bit here, the noise figure equation up here deals only with the linear equivalence to the decibel scale. So in other words, nothing up here is in decibels. It's all converted over to a linear number. So the FN stands for the total noise factor. Now, once you get that number, then you go back down here and you take this equation right here, and then you can get the noise figure in dB of the total system. This includes the preamp stages, the filters, the losses of the cable coming down, and the SDR. Now, I don't know which SDR we're talking about here, so I just guessed and took a typical number for the little SPY SDR, which I had a number for. So anyway, the first stage, this one is the noise, total noise factor that you're looking for. The next one is the noise factor of the first preamplifier stage. The second, this is the second stage right here, and that amounts to a noise figure of the second stage -1 divided by the gain of the first stage. Now, and also you sometimes have to account for the loss of the filter in between the first and second stage. I'll show you that here in a second. And then we go on to the third stage, which would be the typical SDR in our case. You know, the one of the whichever one we decide to use at the time. So F here with the parentheses mean F1, F2, F3, and G is a stage power gain. These are both, F's are all noise factor, and the stage power gain is also in the linear units. In other words, if you had a 20 dB power gain, that would be a gain of 100. So you'd put 100 in here rather than the dB. Did somebody have a question or comment? Okay. Now here are the equations down here. So noise factor is equal to the noise figure in dB divided by 10 and 10 raised to that number. So for instance, if you had a 3 dB noise figure and divide that by 10, that's 0.3. And if you raise 10 to 0.3, you come out with a noise factor of 2. So that's in converting decibels in your head to noise factor, or to the numerical equivalent factor. You simply only have to remember two numbers. 3 dB is equal to a factor of 2, and 10 dB is equal to a factor of 10. And then you can figure out everything from there in your head, but we'll go over that some other time. The gain, of course, is computed the same way. And the noise figure, getting back from noise factor back to noise figure, is done with this last equation down here. So this equation does not deal with any dBs. So you got to convert everything down here and then plug it in, and then take this number that you get when you're all done and convert it back to the real noise figure. So that's the equation right there. Now let's go on to the second stage here, the second slide. These are 4 places where you can go on the internet and get that, get an equation solver right on the screen. It'll help you out, and we'll make that available on the website, I guess, or something like that. But anyway, I use this last one down here as being the one I use to calculate all these numbers. Understand that these sites also have a lot of other calculators related to RF design. So you have a good time just going over and looking at these sites. They're very, very helpful. Going down to the third slide then. So our current preamp example, we have a two-stage 365 megahertz preamp that resides right up at the right behind the 4-turn helix that I use right now, and that's on this frequency. The stage 1 is a mini circuits amplifier with a 0.4 dB noise figure, and 22 dB of gain. Then I go through a bandpass filter, which actually is comprised of two filters, a low pass and a high pass, so that we come up with a fairly good bandwidth of about 100 megahertz up there. And that I just put in a number 2 dB loss because there is a little bit of ripple to it. So anyway, we'll use that number right there. Now the second stage also resides up at the feed, and that is another mini circuits amplifier following the filter, and that has a 1 dB noise figure with a 20 dB gain. Then we have to add in or take account of the line loss, which at this frequency down here is about 4 dB. We have about 200 feet of Heliax, but it's a Heliax RG213 combination as we get around the axis movement. And then we have a receiver. This is a typical kind of receiver SDR that has about a 5 dB noise figure. We don't have to associate a gain with that, but just the noise figure. And the results, overall noise figure, with this up in the front end, a 0.4 dB noise figure up at the front end attached to the antenna, the total system noise figure with all these losses and gains and everything still comes out to be 0.41 dB, which is very good. It's about 29 degrees Kelvin temperature. And so that's, we did see some pulsars, and we were able to detect them here. But we have a lot of more interference as we get time with this thing and watch the signals on the band. Turns out it's a lot noisier than I had ever expected. So we may have to move again to find another frequency that's quieter, but nonetheless, the equipment did work okay.
Ray, can I ask a question?
Sure.
Why do we need the second amplifier?
Very good. In this particular case, we might not need it, but the more gain that you have up here masks this loss coming down the coax. Now, when we're up at 1420, we have about 10 dB worth of loss. So, for instance, this last noise figure contribution would be only about 10 dB gain, that we'd actually lose 10 of that coming down the coax. On this particular frequency, I'm estimating we have about 4 dB loss total. So it just turned out to be that I wanted this noise figure or this gain combination to be fixed, and we could change filters simply. These are very wideband amplifiers. So by using a bandpass filter, I restrict it to keep some other interfering signals from causing intermod problems. And so I want to make up the gain of this too, because that subtracts from this gain up here. And that's a little bit less gain than I'd like to. I'd really like to see about 40 dB gain, typically out of my preamps up there. And quite a few of the commercial ones we have at least 30 dB gain. But on mine, I like to build in about 40 dB. And you're going to see the result of what I'm talking about here in the next couple of slides.
Say, Ray,
Yeah.
this is Bill. Let me ask a couple of dumb questions. Does the bandpass filter have any noise figure?
No, it's a loss.
So it's just a loss.
It's
So
not, it does not have any gain. Yeah.
okay.
It's just, ideally speaking, they're lossless components. They're capacitors and inductors.
Okay.
And they're lossless, but that's in real fact, it's not the case, but it's very small if you build them right. You can buy the bandpass filters as well, but
Because when we talk
just have a little
about
bit of loss.
okay, well, when we talk about a noise reference, we're always talking about a resistor, and so there's a non-gain element that has a noise figure, right?
Sure, right. But in this case, we don't really have any resistor in front of the front preamplifier.
Yeah. So,
And so therefore it's below, it normally would be, if you think of the noise temperature of all the parts up there. If it were a resistor, it would have a Kelvin temperature of 290, but without having any resistor components in front of it and any lossy components, the noise figure of modern day transistors and ICs can get down well below 1 dB. And in fact, we can get down to much lower than what we actually have right now. But these are fairly common off-the-shelf parts.
Okay.
So then we go on. That's our current preamplifier up in the dish. But I wanted to add a 6-meter example that Paul is using down there. So Paul has an advanced or applied receiver research, advanced receiver research, I think, preamp. And it's about a 0.5 dB noise figure and 24 dB a gain. It's a model number P50VDG. And so what I'm going to do is I'm going to run this equation with no attenuator following the preamplifier, a 10 dB, 15, 20, and 24 dB attenuator after the preamp. Most often these guys want to get rid of some of the gain because they don't need the extra gain. So the SDR noise figure, SDR sharp or SPI, is about 3.5 dB. And so here, using the results of these calculators, the results of no attenuator after the preamp, using one of these preamps, comes out to be with a 0.5 dB noise figure. It only degrades it by 0.2 dB. That's with 24 dB gain and a 3.5 dB noise figure following it. The overall system noise figure is 0.52 dB. If you have a 10 dB attenuator behind that amplifier, preamplifier, then the noise figure degrades to 0.69 dB. If you put a 15 dB attenuator, it degrades to 1.1 dB. 20 dB noise pad will degrade the overall noise figure to 2.1 dB. And if you use a 24 dB pad and you have a 24 dB gain, but you get rid of all of the gain, the noise figure is now worse than the receiver alone. In other words, you've lost 0.2 dB. So that's the unusual characteristics. You no longer have this 0.5 dB noise figure preamp if you kill a lot of gain behind it, is what I'm saying. And so I know that some of the guys don't understand that. Go ahead.
Hey, Ray.
Yeah.
Just as an FYI, I have a 10 dB attenuator after the preamp. And
okay,
the reason I put that in there was I was told that the SDR front end can overload if you put too much gain from the preamp into it. That's why I put it there, but maybe I don't need it.
Actually, no, that is true. You're more sensitive than to overload. The more gain you have, each stage can actually overload, and that's why I put the filter between the first and second stage up there. Is just to keep other signals, because these are very wideband preamplifiers that we use. I don't know about this particular one. This one is probably not. That has already some selectivity built into it, but that just shows you that you no longer have this 0.5 dB noise figure that you thought you did. But on 6 meters, it doesn't make any difference whatsoever anyway, because the noise coming in on the antenna determines the signal to noise ratio. It's much higher than this 3.5 dB noise figure of the SDR. So that being the case, noise figure is not an issue. You can't use it. So going on a little bit, if that answer your question?
Yep.
Hope so. Okay. Let's
I have
go
a
on
small
down.
comment, Ray.
Yeah, go ahead.
Yeah, I just want to comment that, what case about the SDR and 10 dB pad and the noise figure and all that. Well, the golden rule is more more gain you have and more noise. So that's, you can't just get rid of that physics. But if SDR pole is maximized gain, so if you have all the settings and put an auto gain, you're actually compromising your overall noise figure. So you have to switch to the manual, get rid of 10 dB pad, and maximize your gain out of the preamplifier, because the preamplifier noise figure is less than the SDR receiver. So you always maximize the receiver on the front end towards the antenna, and reduce, as Ray's saying, the signal at the receiver. In your case, 10 dB is actually doing worse. So that's what my suggestion would be.
Yeah, okay. Yeah, the noise level on the speaker, on the output of the receiver, goes up, but the actual sensitivity, the front end noise figure, is what you're worried about. That's this guy up here. That follows the preamp if you've got enough gain after it, and don't destroy it. Just don't destroy the gain. But even 10 dB pad doesn't ruin it very much. Like I say, on 6 meters, it doesn't make a difference anyway, because there's so much noise on the band anyway when you get down to these kind of noise figures. Let me go on to the next one here. Okay, stuff to remember. The first stage has no filtering on the input, so any and all signals present might cause overdriving, resulting in intermodulation issues. And that's something that we faced down at Haswell. And particularly this last time, we were looking at a lot of aircraft flying over, and they, when they transmitted, I'd never seen them before, but they were down there the other day. And when we were trying to do pulsars, and I don't think they were strong enough to do intermod, because any signal that overdrives the amplifier, then you get everything that's coming in the front end intermods. So be careful of that. The second stage can be overdriven if it's not filtered first by the interstage filter, and there you're getting rid of anything, in our case, below about 300 megahertz, and getting rid of everything above 400 megahertz. But if anything in that range can certainly cause overdriving of particularly the second stage and the SDR down in the building. Any transmitter at the site could overload the preamp, even with interstage filtering. So down there, we always have to, we have an AM station down there. That's why we have it turned off when we're actually trying to do pulsar work, because we could be susceptible to, say, even 6 meters getting through the filter up there. It's not that good a filter. Now, continue. In this case, a potential transmitter is any source putting out a milliwatt or less. In other words, you can have very small transmitters, even in computers, down there, and have enough energy to get up there. And when we get the cascaded gain, if it happens to put out a signal within the passband 200 to 300 megahertz, or 300 to 400 megahertz in this case, excuse me, it could cause intermod issues up there. It could overdrive the actual later on stages. Any signal that causes a stage to overdrive causes all signals to mix, producing many spurs. And there are lots of signals coming in there. So once you overdrive one of the stages somewhere, you get a lot of mixing action, and it gets pretty noisy. So that's basically, I think, what I wanted to talk about. I have, is there any questions on this? If not, then I want to show you a couple of things that I've been doing here at my own ham station. And that's, I do radio astronomy work here, and I have a 12-foot dish. It's an all metal dish that we used at radio stations for a while. And this is looking at 1420 megahertz. This is a total power program. And you'll notice a bump right here, because this normally should go real smoothly right through here and back up. So these down here are from part of the galaxy that's moving away from us. And so I was looking at my antenna, not at the core of the galaxy, but out toward the edges of the galaxy through the Milky Way. And that's the hydrogen that I got. In fact, it actually is higher than the hydrogen I got from some of the other looking in toward the center of the galaxy. Surprisingly enough, I didn't expect that, but that's what it shows. So you see some hydrogen here, and if you put your cursor on this when it's live, this tells you what the amplitude is and what the frequency is, and it can even tell you down here what the speed of the hydrogen is moving either away from you in this area or moving toward you over in this area. So this is higher in frequency, this is lower in frequency. So that's a typical run that I did Saturday evening. And the next one I've got here, and this is one that you can have fun with. This is noise from the sun at 1420. And so this is about 14 dB from here up to here. That's a fairly good amount of sun noise. I think I could tweak that and get a little bit more, but that's not too bad right now. And a little side lobe on the antenna right here, but nothing on the front side. I was surprised because when I change feeds, I get other side lobes on it. But with this particular feed, which is a horn feed at 1420, I get just this little bump on the outside here. And so I was real happy with that. This is much better than the log periodic I used for a long time because I was looking at other frequencies as well. But the noise that I got from the sun using the log periodic was only about 5 or 6 dB at the most. And this one's 14 with the horn feed. So much better feed. And on to the future. And I think that's it, Myron. Thank you.
Ray, what was the SDR that you're using for these plots?
For this one right here,
Yeah.
this plot is a Newelec little SDR, just a little dongle. It's the same as the RTL SDR dongles, but it's Newelec's version of it. It's a little better than the normal ones that you get.
Yeah.
And it's just the smallest one. Yeah, but that's all it was. And the total power program.
And do you have the preamps in front of it, or what's the configuration?
Yes, it does have a preamp right out at the antenna and about 30 feet of line coming in, maybe a little bit more. But there is a preamp right up there. It is a Newelec preamp that they sell. It has about 40 dB worth of gain with a SAW filter in the middle of it. In other words, 2 stages with the SAW filter, very similar to what I build down for the site. And it has a noise figure of about a half a dB and a gain of like almost 40, right close to 40 dB.
Okay.
Yeah.
What are your broadband band preamp? What's the frequency coverage on that?
Well, in this particular case, the coverage is much narrower because it's only for hydrogen.
Okay.
And the bandwidth is about 30 megahertz, I think, something like that on this frequency.
Are you using hardline for your coax?
No, you gave me the hardline, the cable, I think. It's LMR 400.
600. Big.
Mostly.
Big yeah, LMR 600, the big stuff. Anyway, thanks a lot, Ray. Any more questions for Ray? Ray does all our antenna building, preamp installing for all the listening devices up there when we switch frequencies. And what's the schedule now for the feeds? You going to leave the feed up there, your current feed, until we change it out for EVE?
Well, I may change it again, and I may, because of some conversation with Dan when we did the last Pulsar run, I may go and switch that to the 420 feed, the one that we originally got the first Pulsars with.
Okay.
The dual dipole one.
Okay.
Hey, Ray,
Yeah, I may do that. Yeah.
Ray, you were talking about 365 megahertz.
Correct.
Did you have any success hearing the pulsar that was originally found by what's her name? Can't think of her
Jocelyn
name.
Bell.
Jocelyn Bell.
No, we did not get that one. We did try, or we tried one of them. Dan could correct me on that. We did try one of them, another lower pulsar. In fact, I think we tried a couple, and we didn't didn't get any other pulsars other than our same calibration pulsar that we always use. We call the 54 pulsar.
Right. Okay, just interested.
Yeah, the 377, we were listening down there during the open house, and there was an air traffic control ATC center. Denver Center has a remote station down there just north of Los Animas, and they were transmitting on 377, or was it 375.175, something like that. Anyway, they had a remote down there, remote transmitter, and it kicked out quite a good signal. Then we were also hearing a few megahertz away some military aircraft conducting the air-to-air maneuvers with several, might have been AWACS or tankers or fighters. You could hear that conversation going on as well. So there is activity up in that portion of the band.
Yeah, was that little station, was that north of La Junta or north of Los Animas?
Los Animas.
Okay,
Or I get those guys mixed up down there. Might have been Lana.
okay. Yeah, I thought that's what you said originally. Oh,
Yeah, Lana.
okay, very good. Thank you.
Yeah, you can find it on an IFR en route chart. All right, well, Glenn and Lewis, you guys are up next. So you got the screen. You can go for it and give us your presentation there.
Okay, does everybody see that okay?
Yep. It's good.
Okay, great. So this will be a really quick presentation, one chart. All I'm really going to talk about is what we're going to be doing down at the site tomorrow. We're going to travel down tomorrow morning, and we'll be performing these following 5 tasks. The main task for us down there is to take the new operator console PC, which Paul Sabone got for us, and we're going to install that and replace the laptop that's sitting down there. And once we do the replacement of the PC, then we're going to check out both the 12-bit and the 16-bit systems, the automatic and manual processing. I already have those installed on the box here, and I've checked it out with the simulators and thing. So I'm hoping that'll be a relatively easy thing to do once we get down there, but you never know what's going to happen. So that's the main thing we want to do once we get down there. In conjunction with that is that on the 16-bit software, there's some software fixes for ambiguous zone processing and for Venus tracking. So we're going to definitely check out the ambiguous zone to ensure that it's working correctly. The ambiguous zone is where you slew into a place between 15 degrees on either side of 0. And if you bring it down or bring it up, the software gets confused. And we've made a fix to allow the operator, if they do bring it down or bring it back up, to move out of that area. So we'll be verifying that fix tomorrow. And then the next thing is we're going to collect some mount characteristics data. And that data we're going to collect kind of flows into what our new design for our track processing. And Lewis has got a presentation after this my presentation that he'll go through about 10 charts about the modifications that we're looking at for track processing. Then there's this other thing that I've just recently started calling a combo system. And what that is the actual Raspberry Pi software and the operator console software, the client and server software, both of those will be running on the new PC that we're taking down there. And I've got that up and running here. I've made some minor software modifications. And what I want to do down there is I want to run the CPU utilization program to see how much CPU we're using by having both of those systems running simultaneously on a single box. I was running that today a little bit, and the CPU utilization tool indicates there's 4 CPUs, and we're making use of 2 of the 4 right now. So but that looks pretty good, but we'll see what it looks like once I get down there. Now, we may or may not want to get rid of the 16-bit Raspberry Pi. There are definitely some uses for it where we could use it as a display device or something, but we can talk about that down the road. I just wanted to see if it was feasible to see if we could get rid of the Raspberry Pi if we were worried about RFI kind of things for Dan. So I'll be looking at that. And then the other thing we're going to look at if we have time is we purchased this this industrial non-managed PoE internet switch. It's got 4 ports on it. We can use it for the encoders, and their operation range is much better than the one that we have up there right now. It runs from like -40 Fahrenheit to 174 degrees Fahrenheit. So we're going to look at one to see if there's a power coming off the power supply that we have in that enclosure. And if that isn't there, we need to look to see how long we're going to need to run maybe an extension cord or something for that power. So that's the other thing we're going to do. And if we do have time and if everything goes well, we may go ahead and install that switch. So those are the things that we're looking at down at the site tomorrow. Any questions on that at all? Okay, I'll bring up Lewis's presentation. And okay, can everybody see that?
Yep.
Called tracking modifications.
Yes.
Okay, are you ready, Lewis?
Yep, go to the agenda page and there's been some question. We've been looking at upgrading the tracking algorithm over the fall, and there've been some questions on it. So wanted to kind of get out in front of the group what we've been looking at, and see if there are any questions, concerns, whatever. I'm probably going to try to go fairly quickly here so we don't take up too much time, but please ask any questions whenever you have one. Kind of this first subject would be basically to take a quick look at the current tracking approach so we can contrast that with what the modifications we're talking about making. And once we've kind of described the modified approach, then we want to look at some kind of performance considerations, and that really comes down to looking at the tracking signal loss using the updated algorithm, and also looking at how frequently the mount is commanded. And what I've listed here is step, drift, interval, and as we get into, you'll see why that name is there. So that's been a concern that to try to minimize how often we're updating the mount position. And so we'll talk about how this algorithm affects that. And then what it really comes down to in the end is there's a trade-off between you won't reduce signal loss, you'll incur a reduced or increased commanding frequency. If you can tolerate a higher signal loss, then you can command the mount at a reduced frequency, and the slides will indicate why that is. So I think I want to get to this first slide on the current tracking approach. Just as a brief history, this current capability has been out in the field. I don't remember exactly when it was fielded, but it was 3 to 4 years ago. And prior to the fielding of this, the mount was positioned in tracking was conducted using the front panel of the manual control capability, and it was pretty tedious to do. So we tried to field fairly quickly a capability that would have the computer control that, and we basically mimicked what the operators were doing when they were throwing the switches to position the mount where they were. And so with the idea that kind of a more sophisticated approach would be taken after that. Well, it's now 3 or 4 years later, and so we've started finally getting around to it. So on this page, this plot is a plot of tracking for one axis an object that's moving at a fixed rate. And so just for explanation, the x-axis here is time, and then the y-axis is the position of the object. So in this case, the object's moving, or target's moving at a fixed rate. And then you'll notice there's some dotted lines on either side of the tree. And those are really, that's the threshold where we're trying to maintain the axis between those two upper and lower thresholds are balanced. So the way the tracking algorithm works right now is, let me see, start here where the axis slew is initiated when pointing error threshold exceeded. Basically, the axis is at 0 rate at that prior to that, and the object is basically drifting, and since the axis is 0 rates, the object is gradually getting farther ahead of the axis. At the time that the error threshold between where the axis is pointing and the object hits the threshold, then we turn on the mount, and it's turned on at a fixed rate. And then when the mount gets inside of the threshold, we turn it back off. What, a subtlety that happens here is our update loop is running at once per second. And and for the axis step rate is 0.1 degree for the azimuth and 0.05 for elevation. So basically what happens is that step it'll step for 1 second and then turn the mount off. You'll notice that the axis position basically never even gets to the object position, much less goes over on the other side of it. And then once it's inside, we set the rates back to 0, and then again go back into a drift type mode. And it'll drift until it hits threshold again. That cycle just repeats over and over. And so you can see from the diagram with this approach, there's a pointing bias. The axis is always below or in effect behind the object. Now, if the object was going negative rates with this, with the trajectory pointing down, it'd be the opposite. It'd always be somewhat above it. The other effect of this is that the axis commanding frequency is higher than necessary for accuracy. If when we powered the axis on, it went farther and closer towards the target trajectory, or even beyond, then the drift phase would last longer, and that would reduce the commanding frequency. So, and commanding frequency has been a concern with respect to wear and tear on the mount. So that's the current approach. The software receives position data from the Pi at 10 times a second, but the tracking update loop currently only runs once per second. And there are some reasons for that. We'll probably be able to run the modified loop at a higher rate when we move the software down onto the new machine. Right now, we let me see. Excuse me. We have the tracking threshold set to 0.1 degree for both axes, and that's the way it's been pretty much from the beginning. We use a higher step rate for the azimuth than the elevation. I think early on we were using 0.1 for the elevation, but it seemed to cause some instabilities. So we dropped it. It caused the instability and overshooting and such. So we decreased that to 0.05. I believe that was done before the 16-bit encoders were added, but
Yeah, it was.
so when we went to the 16-bit encoders, we did not change any of these tracking parameters. They're the same as they were. And basically, so the track basically works as it did with the 12-bit. The big difference in terms of, and it's not really a large difference, is it can more accurately discern when it crosses, the tracking threshold is really what happens with the 16-bit encoders. So we'll go on to the next slide here. And so we're going to contrast the old approach with this new modified approach, and kind of label it the step drift tracking, because basically it consists of a cycle of stepping and then drifting. So, which the current algorithm does, but the difference is the algorithm is modified to when it steps to go over all the way to the opposite boundary, opposite threshold. And so that maximizes the amount of time that you can get drifting. So just as what we see, the box with axis drift interval, it shows that when the axis rates are 0, the target catches up and passes the axis position. And then the duration for that is the object is actually moving 2 thresholds worth of difference, and it's moving at the target rate. So the duration of that drift is 2 times the threshold divided by the target rate. So from that, we can see the duration of that interval is directly related to both the threshold and the target rate. And I'll show some slides later on that, show that relationship. Then at the point where the drift crosses the threshold, then we turn the mount on at the step rate and step up to the boundary. In this case, we're thinking right now that we'll step both axes at 0.05. The primary reason for 0.05 really is that's the slowest rate that the elevation axis can move at without being turned off. So the step interval duration is similar. The formula is similar, except that it's basically the threshold distance is being crossed at the rate of the slew rate minus the target rate, since the axis is catching up with the target. It has to, you have to subtract off that rate. The net result is the slew rate or step rate is much higher than the target rate, so the step phase is much shorter in duration in general. And so the overall duration for the step and the drift phase is mostly driven by the drift phase. So in this example, I was just, you can see the statistics or the parameters for this particular track. The target rate is 0.004 in degrees per second, so that's pretty slow. We'll talk about what the expected rates are here in a few slides, but that's beyond what you'll ever see on the elevation axis, but that's a fairly nominal value for the azimuth axis. The slew rate of 0.05, and then threshold of 0.1. While it's not relevant on this slide, we'll start it later, but it's using a half power bandwidth of 0.81, which is really the bandwidth for a 1420 megahertz signal. In this track, what we see is a max signal loss for this one axis would be 0.183. The duration of the step time is 4.3 seconds, and then the duration of the drift is 50 seconds. So the overall cycle time is about 54 seconds for this one. And one of the things is that with 0.05 slew rate, that's roughly 10 times as fast as our actual tracking rates that mostly we need to achieve. So that means that in general, we're going to have duty cycle of about 10% on and 90% off for the mount, depending on the mount rate. Let me see.
So Louis, you're saying that the parameters, the outside parameters of the what do you call it? The threshold.
Right.
How far is that from the center line or the track of the object?
The 0.1 is the distance from the object line to the dotted line.
That's 0.1 degrees.
0.1 degrees, and that's in a vertical direction is the way. Like for instance, on the 50 time mark, you take that vertical mark, the distance from the blue line down to the blue dotted line is 0.1, and then the distance from the blue line up to the yellow dotted line is 0.1. And basically that's the position, and that position moves along with the object. Is that make sense? Or
yeah, it does. Well, that's what I'm wondering is because our 3 dB focal zone of the dish is around 0.8 degrees at 1420.
Right. I think the next slide might
yeah.
So this is just an example.
Show the kind of, I think, what you're getting at.
Yeah, go ahead. I'll shut up.
Yeah, I think that previous slide was only for one axis, and you have two axes. So this slide shows the pointing error for both axes, and just to kind of describe it, you see the 3 dB line or circle, and that's
that's the outside circle, right? Yeah,
that's the outside one. I also plotted some, lower dB circles just for reference, and so the green line is actually the threshold. So the upper and lower horizontal green lines are the thresholds for the elevation, and then the left and right green lines are the thresholds for the azimuth. And with this algorithm, what it's supposed to do is to keep the amount within that square, basically. And you show, and this is with 0.1 here at 1420. So it shows that well, we talked about what the loss was, and we'll see in the next slide even better description of what the loss are, but it's around 0.17 or so on this spot. So
0.17 dB.
Right.
Why are we trying to do this so accurately?
Bill, this is an example. It is not what we're trying to do.
Okay.
This is just an example.
Well, okay. All right.
what we're trying to set this up is so you can vary that threshold.
Yeah.
And so, in fact, I'll show some slides, some plots later on at different thresholds and what it means with respect to signal loss and with respect to how frequently we're commanding the mount. And that's the trade, your trade accuracy versus how frequently. And, you know, you might make a different trade depending on whatever the mission you're trying to run. So, but I chose 0.1 in this case because that's really the threshold that we've been running with. And I think it's, I would call it a happy compromise between the two. But, you know, that there may be other choices. So,
Well, let me just make a point here. The reason I pushed this so hard for the last year and a half or 2 years is we're driving the mount very rapidly. We're driving the mount very often, and we're literally putting a lot of wear on it that we don't need to put on it. And if we're within a 1 dB threshold, I would think that we'd be fine, or even a 2 dB threshold. There's very few applications of this where I can see that we want to be down at this accuracy level. And the trade-off is that we're driving the mount so often that we're wearing out all the mechanisms.
yeah, what I would, one of the point I would like to make is if we run this algorithm at the same threshold as the current one, it'll roughly drive them out about half as frequently just from going to this new algorithm.
Yeah, half's not good enough.
And
not from my
then,
viewpoint.
Well, I'm not trying to set a threshold. We're trying to come up with a system that'll allow the threshold to be set.
Yeah.
And there are we'll see the plots that show the trade-off, and it's not necessarily a directly linear relationship. So, but you'll see them later on, and give you information about threshold versus update rate.
Okay.
I agree that I think this method is undesirable from the standpoint that we're turning them out on and off. If we could run it at slower rates, then I think that would be less wear and tear. That's just not available option, particularly with elevation axis. And we're proposing to use this for both elevation and azimuth, just for consistency. So that was the points I was wanting to make about this slide. So we're going to look at the signal loss in a little more detail, just so everybody will understand what's happening. This is the same example as the previous foresight view, is just presented in a different plot method. And so basically in the example, the as target rate was 5,000th of a degree per second, and the elevation was 2,000 degree per second. And those are fairly nominal rates for as and now. Then you can, when you look at the commanding interval, it's about, because the as is running faster, it's running, in this case, at 44.4 seconds. And the elevation is quite a bit slower, and so its update intervals around 104 seconds. So what this means is down below, the lower chart shows the pointing error in the blue. And then in the red or orange, it shows the loss. And these are 2D values, not just due to one axis. So, you know, the error in each axis combines to create a larger error than either one of those axes. And basically it combines using, you take the overall offsite foresight error using Pythagorean equation, and then you apply that off foresight error through this tracking signal loss equation, which is a pretty standard equation. And that gives you the 2D signal loss. And so just explain the patterns here. It's not just a random noise. It's really, you know, occurs as a very periodic way. Basically what happens is when you're going through the drift phase, you drift from a maximum error. You drift through where the object's very near the foresight, which gives you minimum error, and then you out to the next, the other boundary. And so that gives you this scalloping shape. And there's, since we have two axes, it running that where the target rates are different, we basically have two scallop shapes overlapped and combining in the kind of the short scallop shapes occur when the mount is stepping from one boundary to the other, and that gives you those short ones. So basically what happens, it kind of goes from maximum loss to minimum loss back to maximum loss in a period of, you know, the steps take around 3 or 4 or 5 seconds. So you see you know, a quick change, and then you see a much slower change when you're drifting. So you know, if quick changes cause issues, then this method can potentially cause some issues. It's not just a steady, gentle change.
Right,
And
but
this,
it's still only 0.5 dB as in that lower plot, right? Is that the lower plot is the combined?
the lower plot is the 2 dB, and the max value, it's over on the in the blue box, is the maximum, which occurs around 100 and whatever that is. Can't read that.
If I look at the axes, it looks like 0.3 dB or so is the one over here on the far right hand side is about what, 0.4 dB?
That one is, well, the number is 3.373.
Yeah,
Oh,
in the
okay.
blue box, Bill.
So
Yeah, I see it.
that just, you know, because the as and L can be because of the target rates can be different, this diagram, you know, it'll differ, but the basic scallops, short and long scallops, will be in all of them.
So hypothetically, if I said we could tolerate 1 dB, I'm not saying for everything we could tolerate that, but certainly for EMI and most things we do, we could probably tolerate 1 dB. We could reduce the mount exercise to a third of this, right?
Not sure it's, well, I'm not sure it scales that way. We could revisit that on later charts.
Well, that's why I'm saying we were asking for a way to select that, and I guess you'll get to that. But
well, actually, the way you select it's on this chart, it says signal loss equals 12 times foresight error divided by the high power bandwidth squared. If you rearrange that equation so that you state offsite error as a function of signal loss, then you say, okay, I can tolerate whatever signal loss, you plug it into that equation, and then it tells you what the offsite foresight error you would need to reach that.
right.
And I haven't shown that, but that's how you would do it. It's a pretty straightforward equation.
Bill, I think on the previous page, their dB loss, it showed probably you could go for 0.2 or 0.25 for a 1 dB loss. You know, it was the one with a little box in the center. If you could you roll back to the previous page of the there. So yeah, 0.25. So, you know, technically you could go for like a 0.25 approximately error for a 1 dB loss in this case.
Right.
There is one other flying noise, and that has to do with how the rates of the object in a particular part of the sky.
Right. It varies wherever you are, for sure.
Yeah.
Yeah,
Yeah.
I have a slide to illustrate that. And so what you will not be able to do is say, I want the mount to update every 200 seconds, period. You have to accept that, you know, it'll be based on object rates.
Right.
You
I'm not saying that. What I'm saying is if we could select the bore site size.
Right, and that's, you know, we have not gotten down to implementing those types of features and whatever, but we anticipate doing that. And we would try to do it in what I would expect is, like you say, the operator would specify the amount of loss that he can tolerate in his mission, and the software would select the threshold that would achieve that. But then at that point, you have to accept whatever those
That's fine.
update interval is for that selection.
Yeah. Yeah. And that's going to be, you know, if you select a much larger bore site size, that
Right.
interval is going to increase. And that's what I'm aiming for is I'm just
Right.
afraid we're going to wear the mount out by the time we figure this out.
I don't think that's going to happen. Lynn has this.
Well, we've already broke a chain.
Well, I don't know why that chain broke, and I don't think.
And so there's wear. I mean, every time you drive the mount, there's wear. And just listening to it, we know there's wear. And so what I'm trying to do is say, okay, we've got one thing to play with here. And originally it didn't do this. This happened after we added the algorithm. We actually did have an interim algorithm that took a lot longer between cycles.
This is the algorithm that was built in.
That's the one we've always had.
No, it changed.
Oh, I wrote it.
I'll let it go. Okay. Just that's my input. Okay. We gotta open this up.
Right.
Yeah,
I agree.
Go ahead, Glenn.
Yeah, I wrote all the software that has to do with a lot of this stuff, and I know when we changed it, when we didn't change it. So this is what we basically had. Now there was once upon a time when we were doing stuff with the front panel of the manual mount control. Then you could actually do what you're saying. But
yeah, it wasn't manually done. It was done on the system, but there was an interim system before this particular code level. Or what we have now, not this code level, but what we had now.
Yeah, and Bill, you know, that chain is how many years old? I don't think you can ascribe.
That's not my point. All I know is that we're driving the scope much more often than we need to drive it to get the accuracy that we need. That's all I'm saying.
What one concern I had is it sounded, Louis, it sounded like you said something about describing how many dB we could tolerate. I think it would be more useful for us to describe, you know, how many degrees or tenths of degree off we want to be, because then we can experiment, because that will give us the dB drop off. So I think it'd be more useful for us to be able to describe the arc of error, or arc of I forgot what you called it, threshold, rather than a dB drop off, since that's going to vary for frequency and everything like that. Just
That's right.
allow us to specify an angular.
That's right. That's going to vary for each different feed and frequency that we use.
Yeah.
So, yeah. Roger's right.
Yeah, well, I mean, we're open to anything as far as how the operator communicates to the software. I mean, we can all take a look at it. It's not that big a deal. We just need to pick a solution eventually.
Yep. Okay, I'll shut up now. Go ahead.
You're fine. That's why we're talking.
I think that's the points I wanted to make on that
Okay.
slide. Since we made the point that the target rates are one of the, if not the key driver, well, there's two key drivers, the threshold and target rate. So I wanted to show what kind of target rates we might encounter. And so primarily our primary targets in radio astronomy are beyond the solar system, which means the targets are sidereal rates in general. And so these tables show what azimuth rates would be at a specified elevation in azimuth. So like for instance, at 180 azimuth and let me see, say 0 elevation, the azimuth rate would be 0.0026. And one of the things you'll notice, and particularly on the 180-degree azimuth, as you get higher, the rates get higher. And in fact, when you get close to 90, they get, at 88, I think the max is 0.09, which is pretty high. And so that's the way to read this chart. That upper table shows you, it's really, I've structured it as a heat map. And what I tried to color code it to show really slow rates are in blue. And by slow, it's 0 to 0.002. Kind of semi-slow, I guess you'd call it, is 0.002 to 0.004, and that's in the green area. And then yellow, it's rates between 0.04 and 0.01. And so those are getting faster, and the update cycles will start to grow. And then, the highest rates are above 0.01. And so you can see where in the sky those will occur. And basically for azimuth, just the higher you get in elevation, the rates get higher. So let me see on elevation, the elevation rates, the table works exactly the same, except that it do the elevation rate for a given azimuth combination. And there's a real definite pattern here. It's basically in the east and the west, the rates are the highest. And then along the meridian, 180 and 0, the rates are the lowest. And that really is because it rises in the east. And so it's going up. And then as it crosses a meridian, it's 0 and then starts going back down. So that really explains why. So the range of value for the elevation is the fastest rate in this table is 0.00327. Given the granularity of the table, the max elevation rate might be a little bit higher than that, but will be quite close to that. And the min L rate's 0, whereas on the azimuth, the min az rate is well, it's essentially 0. It's 2/10,000. And the max az rate up to 88 degrees is 0.09. And I've shown it below 85 degrees. It's my opinion, we shouldn't be tracking things up above 80 or 85. So it's getting a little too fast. And let me see. So that's sidereal rates. The other things we track for moon bounce, we track the moon rate. And the moon actually orbits the Earth in the same direction as Earth rotation. So what that really means is its azimuth rates will be slightly, it'll be below the sidereal rates for any given position. One of the things, I think the highest the moon can get here is around 80 degrees. So around 180 as the rates can get fairly high for when you're tracking the moon. Planetary rates are most likely fairly close to sidereal, but that it's going to vary because of the relative position of the Earth and whatever planet you're interested in. So I didn't try to characterize what they're really going to be. So right now, I think the only planet worth talking about tracking is Venus. And some analysis has already been done about rates, you know, around the time that the EVE will be attempted. So that's the rates that we would expect to encounter. This chart is just a plot of the step drift interval as a function of the target rate. And now there's other factor in it is the threshold. So I plotted this at a set of thresholds from a pretty tight threshold to what I consider a fairly loose threshold. So the upper one is the threshold at 0.2. And then the next one down is 0.15 threshold, 0.1, and then 0.05. And the way you can read this chart is that you can take a target rate you're interested in, and just to do one that's easy, 0.005, and you go vertically up until you hit a threshold plot line, and then go across to the y-axis and read off what the interval would be. So if you have a really tight, let's say at 0.005 for a really tight 0.05 threshold, you're going to be, the update interval is going to be around 20-25 seconds. If you run, if you go all the way up to a 0.2 threshold, then, you know, the update interval is going to be around 90 seconds or so. So that's the way you read this chart. What you see is that at the faster rate, the thresholds don't make as much difference as they do at really slow rates. And we're, in terms of elevation, we're probably going to be sitting, most of the time, the rates are going to be around 0.002 to roughly. And so that vertical line is the kind of update intervals that you would encounter there. So it'd be anywhere from 50 to 200, depending on your threshold. Let me see, azimuth, it varies more, but I think it probably, you know, it might cluster more around 0.05 or so. And so you'll see that you can't get as long intervals at that rate. But so just as the thick-way increasing track threshold increases the step drift interval, increasing target rate decreases the step drift interval. So that's about all I was going to say about this chart. We can go on to the next one. So this chart is kind of the final wrap up. This is where we're showing the trade between signal loss, which is a function of threshold, which then in terms of step determines the step drift interval. So in this plot, you can like start from a given signal loss you're interested in, go horizontally across until you hit the target rate of interest, and then drop straight down, and you can read off what the update interval would be. For instance, a 1 dB signal loss come across till you hit the 0.004 degrees per second, drop down, that's, 110 roughly. So, I didn't show some of the higher rates like 0.01 and above, and those just get less frequent. So, but what it does show is you can really get quite infrequent when you're running really slow target rates. But at the higher rates, you don't have as much flexibility.
But correct me if I'm wrong, but this would be, for example, a specific frequency and or feed, because that signal loss is going to change depending on what frequency you're looking at. Is that correct?
I don't. Let me think about that. This doesn't assume a specific, well,
because the beam,
that's
beam's
true.
basically wider.
Because, if you're running at 400 megahertz, you got a huge leeway compared to 1420.
Were all these done at 1420, Liz?
I think this was at 1420. I have to go back and check that. I was kind of basically just doing worst case.
Yeah. And the target rate, we don't really, from the previous slides, the target rate is what the object's moving at, right? So that's going to be whatever it's going to be.
That's correct.
Yeah. Okay.
Right. You have no choice but that. And so in the point I want to make about that is, if you're watching the lights on that panel and see it blink on and off, and you see it blinking more frequently, that doesn't mean the algorithm changed or the parameters changed. That means you're in a different part of the sky where the objects are moving faster.
Right. Different target rate. I get it.
Right. So you can't really just look at that. You got to take into account where it is. And,
yeah.
But the point I was trying to make here is that, because I think you said that you believe this was done for 1420.
Right.
When you do get around to giving us a knob, I think that the angle is more useful than trying to base it on dB, because again, that's going to vary depending on what frequency we're looking at.
Yep.
Well, I guess it depends on how critical signal loss is to you. But in any case, we could allow the operator to specify a threshold. In the software, we do allow them to specify frequency, and it could compute the signal loss for that threshold also. And, he could set, I want to set it to a point, whatever, and then he could see how much he's going to be penalized or not in signal loss.
This is going to get more important as we look for more OH groups, and those are small. That frequency is going to be much higher.
Right. I originally took 1420 as I thought the worst case, and then I realized that Dan was doing some maser work in 1600 and something. So, yeah. I will say is I don't think tracking pulsars with dim ones, you can tolerate 1 dB loss. Especially with these the way it moves around.
Yeah, and we're getting into weaker and weaker pulsars, so
right,
it's going to get critical.
So I agree for moon bounce. As long as you got a lot of margin on your signals, then
yeah.
Well, for some things we have a lot of margin.
Right.
And, you know, if we go to 10 gigahertz, the beam width gets smaller and then it matters more. But at 1420, 1600, it probably, you know, we're probably in overkill. Dan might disagree with me. I don't know, but I think we're in overkill right now.
Well, and we can also, if the knob was an angle, we can experiment and actually characterize what we're seeing.
That's right. Yeah, I don't want the program to tell me what the signal loss is. I want to look that up. I want to specify the beam width. I want to specify the beam width and then go from there, or specify the update angle,
Threshold.
the threshold, and go
Basically
from there.
threshold, how far you want to wander off.
Yeah.
Remembering the rate plays into all this stuff, object rates.
Yeah, but that isn't going to matter if I specify the threshold.
No, it won't.
I mean, sure, at a higher rate, it's going to update more often, but that's fine. I'm accepting that the rate's going to, you know, we're going to update more often with a higher rate. That's totally acceptable because you can't do anything about that.
Exactly.
Right. Ideally, we'd like to have a whole different gear train and be able to drive continuously, but we don't have that. We've got a bang bang control system. And my point is to try to minimize the bang.
Yeah, we're not going to track any low Earth orbit satellites with this thing.
No.
That's, yeah.
Well, what I would say in terms of wear and tear, yeah, actually I was going to talk about slewing to the target, but I kind of forgot it. But when we slew, we command amount on azimuth axis to 0.4 degrees per second, which is about half of the commanding range. And we command elevation to 0.2 degrees per second. Before we get to the target, 3/4 degree from the target, then we command down to the step rate. So that when it ramps down, it's there's not a big jolt at the end when you're stopping in the tracking range. One comment well, it turns out that both of the command or the motor controllers are basically rate controllers, and they handle the ramping up and the ramping down of the rate. So if we command it to 0.4 and we're sitting at 0 rates, it will accelerate the mount up until it gets to the commanded rate, and then, you know, and smooth out the acceleration.
Yes, sometimes it's
Those
better
are
to-
all set. Pardon?
Sometimes it's better to keep it moving than to start, stop, start, stop.
Yeah, we just don't have that option because the minimum rate for the elevation is 0.05 degrees per second. And I believe that is due to the type of motor controller and motor we have. It's a VFD, and those can't run at 0 rates or very near 0 in general. Without the motor controller can actually specify that, but I don't believe the motor is not designed to do that. So basically the motor controller for the elevation axis won't let you go below 0.05. And to go to 0, you have to turn it off. And when you turn it off, then the brakes fire. And that's really undesirable behavior, but it's what we got. And
Hey, one comment I could have here. It's Paul. Alex, when he was changing the chain for the azimuth, he noted that the speed at which that thing turns, just to get a 1 degree change, he had to pull that chain down many, many times in order to get it to move even 1 degree. So if you ran that motor slightly slower, you would get much less starting and stopping. Right now, it's turning at pretty high RPM to turn the dish. If you could slow it down a bit, you could run it continuously, I think.
I think we could run the azimuth close to continuous, but we have, right from our early testing, it looked like the slowest it would run at was around, I don't know, 0.01 or 0.02 degrees per second, which is still above the sidereal rates. I haven't gone back and re-verified that, but at the time, everybody thought it was probably stiction. I don't know if that's really what it was or not, but
Could be.
Is there such a thing? Is there such a thing as a variable speed motor for those?
Well, the whole gear train would have to be, I mean, with enough gearing, you can run, down to
Right.
0. But that's the gearing that's in there. We're stuck with what we've got, and we don't have really a way to change that out. We're basically working with the original gear train, but with different motors. The original motors were counter-rotating 5 horsepower motors with a magnetic eddy current clutch in between them. And so the way they drove the dish was to move that clutch with an amplifier, and the eddy currents would pick up one motor magnetically or the other one. And so they were able to drive very slow rates by keeping the motors running at the same speed. That all got taken out because we had no way to drive that system. All the amplifiers were gone. And when the original founders came into the site, they put the motors that the servo motors that they had in Boulder, and the power controls, the VFD controls that they got from these are the same VFD controls that run things like industrial lines. The guy that did all that work was a employee of the Budweiser plant and did can lines. So you can imagine, 1 million cans running down the line at light speed. That's what he used. So those motors is what we have, unless somebody wants to pony up a proposal for whole new gear train, which would be a massive undertaking. This is what we've got.
Is the azimuth motor a fixed speed motor, or can it be varied?
It can be varied.
So, I mean, one of the super simple ways to, if you wanted to drive the azimuth slower, is because those chain teeth are worn. You're looking at replacing those at some point in time. You can change the gearing ratio.
Yeah, you could change the gearing ratio of the chain.
Yep.
If there's room. But there you could maybe pick up 2-to-1 or something, but you still have this problem where you've got we think it's 65 tons sitting there on those bearings, and we're not even sure what the bearings are. And there is stiction, you got to get, and there's a lot of MO, there's a lot of angular momentum you've got to move to get this thing off at ground zero, right? And so you can only go so slow.
Actually, I'll try to add it to my list if I've got some leftover time tomorrow. I'll try to go up and count the number of teeth on both of those things, since we're going to probably have to replace one of those sooner or later.
I think Alex did that, and I think we have that data.
Alex, Paul, do you have that data?
On the photo, we have numbers, Roger.
You got numbers. Okay, never mind. Saves me some work.
You can still go.
I could what?
You can still go there.
Yeah, if you're curious. But I think we're running, you're probably running it about right for speed, Glenn. I don't see, slowing it down has issues, because right now, I mean, it stalls. You can hear it stall in the azimuth direction. And so, I don't think you can run it much slower. You're muted, Glenn.
This kind of the point why we're going down to the side is we're trying to collect map characteristic data. So look at the logging of the data as the map begins to move, as it goes to where it needs to go, that type of stuff. So we can see if for one, if it's consistent and repetitive, and then using that to help us understand how to drive it.
Yeah.
So that's our plan.
Okay.
And to go back just completely, I think we're going to provide some type of operator interface to allow them to manipulate what they need to get their job done. Basically, if we're chasing the moon, it doesn't make much sense to have a threshold that's real tight. If we're chasing a pulsar, maybe that's something else. But I'm not the person. We're not the people to do that. Someone has to decide what makes the most sense.
Right. Dan says 1 dB sounds pretty good for pulsars.
Okay.
So that's just, doesn't have to be 0.1 dB.
Well, we'll provide the capability if we ever get it done. We're old and volunteers.
Oh, yeah, right. Aren't we all?
How close we are to wrap this up there, Lewis?
We got one more chart, I think.
Yeah, we got it. This is just the kind of a high level plan we're working to. We've prototyped this new modified algorithm. I prototyped it in simulated it in Excel, and then Glenn has implemented it in the operational software, although all the mods are not complete. There's enough there, I think, that we can do some testing at the site. He's tested that in Colorado Springs with a simulator, and then tomorrow we want to make some runs with that at the site. Yeah, hopefully we can get all enough information in one trip to be able to verify the approach. Then got to do clean up some additional issues in the code so it'll integrate in with the operational code, and then go back through the test process in Colorado Springs and at the site. So hopefully we can get through this in the next quarter or so, but depends on weather and every other thing. So that's all I had. If there are any more questions,
That sounds really good, guys. Thanks for accommodating all my stupid questions.
Glenn and Lewis, you guys have done a super job on this stuff. It's just been such an improvement all the way through. I remember twisting the knobs to track. So
it was like Pac-Man.
Oh yeah, it was a fun game, but it got tiresome after a while,
Yeah.
So
yeah, I call it Zen meditation.
much like that, yeah.
Well, thanks, Lewis. Thanks, Glenn.
Thank you.
Hopefully you have a great trip tomorrow. Weather should be good.
Should be.
And again, really appreciate all you guys are doing. Sometime we might be able to consolidate some of this discussion into a different group, since there's a lot of detail involved with this, that a lot of good input from everybody involved. Check out the chat page, chat room too. There might be some information in there you want to look at as well.
Well, you may be right, Myron. It may make more sense to have a different meeting with just a core bunch of people to go through some of the stuff at the correct level.
It's gonna get pretty intense.
Yeah.
For those may get lost in the conversation somewhere. Okay, moving right along. Alex, how much time do you need for this? We've been running 2 hours already.
Well, I'll try to be quick.
Well, we got another. Yeah, that's fine. Go ahead and do what you need to do. And then we got another meeting scheduled later on this week for some other core groups. But go ahead.
All right. Just gonna share. You see it, right?
Yep.
I just got pretty quickly with the current status, what overall timeline, what do we have for EVE25? So a couple points, couple things I want to mention. First is I had about 3 weeks delay in one part. That was a driver from overseas. I didn't expect they're gonna arrive a second week of January. When we ordered that around like a second or third week of November. So that kind of postponed all my TX module full assembly. So we kind of like 2 weeks shifted, but it's still, we have a plenty time to complete everything. So as you can see, the red line, if you clearly see the red line, vertical one, that's where we at right now. We're ending the week 4 of January 2025. At this point, we should have been able to test the entire system, but as I mentioned earlier, 2 weeks I expedite actually was 4 weeks delay, and I had to expedite, so I kind of saved 2 weeks by doing some work. So overall status is it's almost done. I have only one thing to assemble. It's the final combiner. That is a tricky part, so I kind of postponed till the last minute. I do have a parse, but I need to do a couple things. Ultimately, just a 1-day deal to assemble and then test it with the full system. So I'm planning to go to Denver. I'm going to actually drive my truck from here because the system is expensive. It's fragile. You know, we spent almost 3 months. I can't just simply rely on the shipping companies to deliver that, and I rather drive and take that system with me and also be present for the time of testing. I'm planning this about the second or third week of February with the final test. So I'm not planning to take the system back with me. It will stay at Haswell. I will have probably a few flights, weekend flights to do final system and tuning. This is what we have currently right now. I'll show you the entire system, how we look. And I finished the last thing I finished, it was the feed. And the feed is not the same feed we have currently. It's gonna look same, but is optimized for this particular project. And that's exactly why I didn't want to use it nor modify the existing feed, because it would not work for this system. I'll show you everything later. I'm just in a different computer. I'm going to transfer to my cell phone. As you can see, there's also, we reserve dates for dish use, and there's the 2 blocks are critical. That can be dismissed because we didn't have a chance to test the system there yet. So we're currently we're currently in the evaluation and improvement stage, which we're testing the entire system. So it's just a lot of details. Let me put it this way, the system is complicated. It's not just ordinary system, but any of us can assemble and run successfully EME. It has only one purpose, to bounce signal off Venus. So everything is important. And that's why I'm paying extreme details on the important parts of the subsystems. And there's also a very unique system from the monitoring perspective. I don't think that any amateur radio systems exist in this way. I added more monitoring system modules, and they're included Arduino. So as far as right now, the system fully capable to send about 32 points of telemetry via the fiber optic line. And also I added recently the PTT. So we do not need a hard line for PTT. PTT also included in the fiber optic. So realistically, we just need 2 lines besides the AC, obviously. That would be the coax for IF, which is also can be converted, to be honest, to the fiber optic. It's called RF-OF. Or RF over fiber, and those modules are not expensive anymore, roughly about $400. So you can run everything off the fiber optic, no coax cable needed. So you would not have any losses whatsoever. Since we're not running high power, we're running only IF power, about a watt. So we can use the cheapest one. But I did not add this to this plan because it's kind of good to have it, but we still can use current infrastructure to operate. I'm not gonna go in details and technical details. That's gonna be different engineering meeting this week, but overall, this is what we have. So as I mentioned, I want to travel to Haswell, actually first to Denver to stay in the lab to do full system RF testing because everything else already been tested, included RF receive. The system is very nice. I very like how the noise figure overall of the system, very quiet. And then after that, we'll go to Haswell and live a system there, which I rely on Ray, Roger, give a help to try to fit the system in the hub. So that's going to be at first attempts of installation. That should happen about third or fourth week of the February. We still have a 2 weeks reserved in March for the final tune-ups and anything that happens from now till then, and a third and fourth week would be reserved only for the execution. So that's what comes current status and what we have right now. Any question on that? And obviously, I will provide the dates when I travel, and any volunteers that want to come and witness and participate in the first efforts, please let us know so we can be there.
Hey, Alex, one question I had was, what is our window of opportunity to acquire Venus? We got it here in March.
Right. It's the third week.
It's the third week of March. How far out can we go? Can we go into April or May?
Well, I think the third week is the closest position to Venus towards Earth.
Yes.
And until then, the Venus, it's getting close to the Earth. So on the fourth week, the Venus starts flying away from Earth. So we're going to have probably a few weeks opportunity, but we weren't going to be able to do on the third week. I don't think the fourth week is going to be helpful because it's moving away from us.
Yeah.
But we're going to be staying positive. I am actually personally staying positive. And I want to see the success of this experiment. So third and fourth week we will show, but it doesn't, if we're going to get system earlier, let's say in the second week of the March, nothing stopping and prevents us to execute. As long as the system installed and we have communication infrastructure, the AC power, and we don't have anything that pop just right in the middle and issues that we need to deal with, right? So we can try start anytime. Also, we can also evaluate the system using the from the receive perspective, using the space objects to read the noise.
Middle of the meeting here.
From space perspective, we can use the moon, because we can estimate what
usually
our
we are, but we're
ERP
talking
and
about projects
reflection signal should be
happen in
with this
March,
particular power. So, and that's also evaluated as this.
Make sure
So I'm open
everything's
to
on
come and do
track
experiments besides the EVE itself, where we're gonna have people, witnesses, and documenting everything to understand the system performance.
Yep. Okay.
All right, so I gotta quickly transfer to my cell phone, and then I'll show you the stuff there, what we have currently.
While you're doing that, Bill, the magic date is March the 23rd. That's when the planet is perfectly closest to us, and it'll be close to the sun, but not on the sun. And so I'm thinking a week before and a week after that would be optimal weeks that we would need. But March 23rd is the date.
Okay.
I could give you the time, but I'm not sure now.
That doesn't matter. That's close enough.
Yeah, we'll get more defined dates and get that information out to those who want to participate in the eyes-on test and hopefully a completion of the project.
It's a smoke test, we call it.
Yeah, and of course the smoke will be seen in the building only up on top. All right. I guess we're waiting for some pictures from Alex.
Yeah, I see his picture, but I don't see him on your share screen. So I think you need to
Screen what you
share
got.
maybe. Alex.
Or project it onto the current screen.
Do you hear me here? Can you drop that share? Hello?
What are we trying to do?
It just dropped the share. Unshare.
I dropped it, but let me drop mine.
There we go. Whoop.
No, there we go.
There you
Okay,
go.
now
Go ahead, Alex.
I'm only.
Do you see the camera?
It's very small. But too many people on my screen.
Well,
if you click on his image, it'll go full screen.
Okay, I've just did that. And you're full screen right now.
I mean, if everyone sees, it's okay. If not, this is
It's
no.
good. It's good. It's good.
We see.
Okay, so I just finished yesterday the feed. Feed is fully functional. I just finished the testing. The feed has unique features because I attached the receiver, which we have LNA and a relay inside, which is if you normally assemble or someone assemble the feed, you don't have this configuration because it's normally just a feed without box. The box is a part of the feed. So to minimize the losses and improve the noise figure, as Ray mentioned, is important. So I pay extreme attention. So I did some testing today, the first try, and here we go. What I've got. So let me do this, and if you see the screen. So this is the receive port. So I've got about 30 dB of reflected loss, and the SWR is 1005. I was able to do that. So it's a very good for the receive. It's actually better than we have for EME. And then also another thing is we have a 716 connector here for the transmit, which the current feed does not have. So this is just not just the complete system. It has the scalar ring right here, and then is also going to have a flare here. So it's for ultimate performance. So feed is done. It's a good thing. It took me 2 days to finish it. So here's the entire system that's currently under test. From the previous presentation, I did not have another module. So we have 2 telemetry modules. We have also Arduino built in here. This is the whole brain of the system. It has more features than any amateur radio EME systems combined. It has so many different things to do. I added capabilities of 13 centimeters. It's a fully remote. You can switch 2 bands without doing anything. It's all relays, everything switching mathematically. All need to be added is just the amplifier. So this is the final system that I was waiting for since November. It finally arrived. This is the driver that drives the entire system. So as you can see, here's a combiner and there's electronics. Everything, by the way, it has a protection. The module, it's completely remote, so you can turn on and off. It has built-in protection. You also read the power reflected, and the forward power is also goes to here and right in the software. This is the operational software. I'm going to have a training to train people how to do that. All these points, all telemetry points right here, which is the power voltages. Right now, let's see, like a reading 27 volts. And then you also have a digital inputs, which tells you, do I have a lock or I don't have a GPS lock? Do I have a PTT on? Do I have an output transmit on? And also the sensors that are reading the voltages as well as the temperatures. So I'm utilizing 16 temperature sensors. You just imagine what is a 16 temperature sensors. Even every single sub-module of power system, like also output for the, as you can see, here's the sensor on input, the sensor output. So I'm gonna flip this on the back. So this is the back of the system. This is the 220 volts distribution. This is 2 power supplies. This is RF outputs, the temperature sensor. So everything is complete. I've done a lot of 3D printing. So the system has a special 3D printer, 3D printed protection caps that covering the important stuff, because nobody want to attach to 50 volts and 60 amps. That's not going to be pleasant because that's already hurts. So I also 3D printed some protective covers for the sensitive systems. So it's good when you have 3D printer because you can always 3D print something that's very unique and specific to the case, like this holder for the sensor. Anyways, this is how system looks, and everything comes through the one fiber optic line. In my case, is the fiber optic line that controls the entire system. I would never imagine I'm going to run an entire system that costs a lot just through the one fiber optic line. It's reliable. I've been running the system for days nonstop. As you can see, it's been running since yesterday morning, and to understand, do I have any problems with the telemetry or anything else? So anyway, this is RF, a module complete, done. It's a fully remote control. Paul, for your case, I put inside the loads to terminator. So we no longer have a problem with the broken lines. So you can always remotely switch this module to internal terminator and verify SWR internally. So it has all capabilities. In case if voltage drops or something happens, the internal system default terminates to 50 ohms. So everything is terminated, and we don't have open lines for the transmit line. So a lot of protection that you normally don't do this, but a 3D system is a commercial unit for us. So it has all these features that amateur radio system does not have. So anyway, that's overall what I have here. I actually built every single cable. Every single cable for the system is complete. Also have a remote relative humidity and the temperature sensor for outside. I think someone asked me before. I think Dan asked me before if we can add this. Yes, we can measure temperature of the feed or overall the hub temperature when we point the system to the sun. So I added that. The relative humidity added just in case if we have a humidity and 80% or more, the system could be shut off automatically. Anyway, I'm not going to go through details. I'm done here.
Alex.
Yes.
So you don't need, it sounds like you don't need an Ethernet cable up there, but you need fiber up to the feed.
Yes. We're always talking about the fiber. Fiber always was the main line for us.
Okay.
And also, I did not mention when I added the Arduino, is actually Arduino has a built-in web server. So, and this is connected to the network, and then through the fiber optic goes back here, and then they have another Arduino inside. So the point is, I can send remote commands to the system. So let's say you want to turn the lights on, or you want to turn something on. I have 4 channels to use to remotely switch the systems. So just in case, because we don't have any capabilities right now to do any remote switchings. Before, I had reserved the internet cable to have those physical lines be present to do something. Right now, we don't need this because everything runs to the fiber optic. A fiber optic, keep in mind, is not susceptible to any static. If lightning strikes, we don't really care because the system is fully protected as long as we have a grounding properly at the feed, and there's no losses whatsoever. Any questions?
Yeah, currently we don't, well, we had fiber at one time, but it was kind of proprietary fiber that Skip installed. Are you expecting that we have the fiber to go in there?
Yes.
Good question. Who's
Yeah, we got-
providing this, guys?
We got fiber.
Where do we have fiber, Ray?
Well, up at the feed. We got about 10 or 12 strands of it.
You're talking about the fiber that Skip installed, right?
Yeah, Skip and Steve, yeah.
So we have to reroute that and put that in the building. And
correct.
And we've got to have compatibility and connections with what Alex has.
Well,
Yes.
Yeah, Bill, because from the very beginning of this project, I've been told the fiber optic exist. So the whole system is initially being designed to fiber optic. because all this telemetry, all this communication except RF need to be done through the fiber optic. You know,
Yeah, I hear what you're saying. I'm just
perfectly-
asking the question of our team here on the ground. Do we have that set up? And it looks like we've got some work to do to get that installed. So we need to know what your connectors are and how we're going to attach our fiber to your fiber.
Yeah, we need
I don't know what's
what
existed fiber in there. It goes to the patch panel, I think, or something. All we need is standard SC connector. It's a very standard size of the connector, and this is used for the patches. You know, if you go to any fiber optic systems, they use these cables as a patch. So it has a very standard fiber optic connector. So as long as they can hook this up in that system, and then on the other side is exactly duplicate of the system. This is the replica of the control center of your shack. So this is the fiber that comes in. So anyway, someone has to take a task, because tomorrow, on Wednesday, I was going to talk about the infrastructure, which is built. Paul gonna cover today from the AC perspective, to 20 volt and 110, all that stuff. And we need to have a fiber optic there, and as well that dimensions of this system, we need to verify how we can mount the system inside. So it's not necessarily this module going to be in here. It's the way designed like that, but it also can be used separately. So you can mount somewhere on top or on the side. It doesn't matter. The cable length is enough to be flexible inside the hub. That's probably Roger going to think with Ray what they can do the best to mount this module and that module and the big module in the middle of the hub.
Okay.
Any questions?
Alex, what's the maximum diagonal on that box, and what's its depth?
There's a 17 by 17 inch. It's a cube. It's a 17.
Okay, I guess I can use the Pythagorean theorem.
The feed is 23 inches deep and 17 inches wide, round diameter.
We'll probably need to mount that on the outside of the hub then.
Now,
Yeah, we're having a meeting. We're having a meeting about this on Wednesday, aren't we?
Yeah, let's wait till then.
Yeah, let's wait till then.
Yeah. So it's all, the system is flexible. The bottom line, this box must be inside a hub. This two boxes can be placed outside because they are a wired connection to the main box. So how it's going to be configured, it's the question of whether you're going to come up with the dimensions. But as far as right now, this system overall dimensions would not change.
Yeah, Roger, I thought we were getting some fiber from Martin. He had some. He was making some fiber runs for us. Do we have those?
We have some. Some are still back in New Jersey, but that's not the point. We've got fiber up there that we can repurpose.
But it goes to the trailer.
But it goes to the trailer, so we can pull it out. It's I don't know. I think that's buried. That's not in a conduit.
It's buried.
But I don't think that the connectors are compatible. So we have to look at that.
Probably just run the whole new stuff.
Yeah, just put new fiber in there. That way.
Yeah, I would just get fiber that has compatible connectors and just run it right to the trailer. I mean,
Roger, I will provide the details about the connectors on Wednesday, so you know what the flanges you need to have it. I specifically choose the very cheap fiber. You can buy 100 feet for $10. The fiber cable, it does not have any, you can use this thin one. You don't need to have a big, we're not looking for transmitting gigabytes of data.
Right.
All right. You can pick up just any fiber, make sure that it's protected, because if I'm going to bend this cable now, it's going to be damaged. So make sure you can pull through all this conduit you have without damaging, right? And there's a fiber optic tester on the Amazon that costs $20. We can pull the money from the EVE budget because we need to get this done and have a reliable fiber optic. If I would be you, I would run 2 lines, because just in case if something happens with one line and system would be compromised, we can at least have a use, because you always find use for the fiber optic, always.
Okay, Wednesday.
So
yes,
You have to be concerned about single mode versus multi-mode and the transceivers that go with it. So that's something you have to look at, but you can talk about that on Wednesday. Those are definitely different types of fiber.
Yep.
So you have to look at the fiber type and the
Yeah, this fiber he has is multi-mode.
So you're going to have to figure out with the fiber types and make them all work together.
Okay. Okay, let me give you the update quick on so it's already now 2.5 hours. Real quick on the power. The electrician is there today. He knows that that we're going to have people on site tomorrow, so he's not going to work tomorrow. But he's going to be putting in two 220-volt feeds to the hub, and each one is going to be on a separate breaker, a separate dual breaker by the power panel. There's going to be a 220-volt 50 amp breaker in the building's breaker box, and from there we're going to break it out to two 220 lines and one 110-volt line at about 15 amps for the 110, and each of the 220s are going to be at 20 amps apiece.
Great.
And he should have all this done by the end of the first week of February.
Okay, thanks a lot, Paul. Thanks a lot, Alex. Bill, do you have anything to throw in here before we adjourn on the building?
The only thing I had was just an update that we installed the projector and the whiteboards and the chairs and all that for the high school group, and that's all I have. I'll yield.
Okay. Well, we had a pretty good presentation tonight, covered a lot of topics, and Dan forgoed his briefing till the next time around, and I believe Rick may have a briefing as well coming up on the feed for the next time around. We'll get more into that on the 408 feed, I believe is what you indicated. And we'll discuss that later on. Ray and you can get together and fine tune that one for the next presentation in weeks from tonight. Thanks a lot for everybody joining. You guys can stick around and enjoy the conversation for however long you want to stay here. And thanks again for attending tonight's meeting. We had 30 people in tonight, and up until a few moments ago, we still had about 26. So good attendance. Thanks, Paul, for sticking around. I know you had stuff to get going. So and everyone else, Rob, thanks a lot for the chairs out at the site.
Oh, my pleasure.
They're very comfortable, very useful, and
I'm glad they worked.
and thanks, Glenn, and if you're still there, Lewis, and Phil as well for all the help you guys have been doing. I think they might have checked out already.
I'm still here.
There you are.
Yeah, we'll be down there about 10:30 tomorrow. So.
And Roger, you're going down too?
Yeah, I go down. Bill, are you going to be available tomorrow?
Not to go down.
No, not to go down. Because one of my goals is to try to replace the Wi-Fi with a access point with the same SSIDs and the same passwords that are on the current Wi-Fi. And what I'd like you to do is for you to test to make sure you can see the camera still.
Oh, so you're saying you're going to shut off the Wi-Fi and the modem router and add another box?
No, I'm not going to shut off the modem. I'm going to shut off just the Wi-Fi portion.
That's what I said.
Of on the modem. I mean, on the router,
right,
in the trailer, and then hopefully replace it with a access point in the building. And I want to make sure that you can still see the cameras.
Right now, the cameras are running off the Wi-Fi in the trailer.
Right.
If we do that, I'm not sure that'll work because the cameras are tagged to that particular box.
Well, they're tagged to the network name and the password that box supports. And what I'm going to do is I'm going to duplicate that. on the access point. So
Okay.
to the cameras, it should look exactly the same.
Okay. Yeah, and so what are you gonna do? Where are you gonna put this?
By the window, I hope.
Yeah, probably right in the window.
Yeah.